Good afternoon, everyone, and welcome back to Thermodynamics. In the last couple of classes, we've been talking about how to evaluate open systems. And particularly in the last class, I talked to you about why we might want to ask whether or not a process can happen in real life. Because if we're designing something, sometimes we've got to figure out if what we're proposing is the equivalent of striking a match or something that can physically happen or unstriking a match. Because just balancing the energy and conserving the mass doesn't necessarily guarantee that a process can happen. It has to be moving in the right direction for entropy to be generated. And the way that we figure that out is by running a second law analysis or looking at the second law of thermodynamics. So we had this process that I was saying that we should follow for open systems, where first we draw our control volume, then we ask what happens to the mass, then we ask what happens to the energy. And this is perfectly fine if what you're doing is looking at a process in real life and trying to evaluate whether or not it's efficient. But if you don't know if a process is possible, you need to add a fourth step here to make sure that you're burning firewood, right? You're doing something that's admissible, something that's generating entropy, or creating firewood from a bunch of mass and a bunch of heat and some ashes. So there is a natural direction that different processes follow. And in order to figure that out, we have to do a second law analysis. We have to show that the amount of entropy in the universe is increasing with the process that you're proposing or the process that you're evaluating. Because if the entropy in the universe is decreasing as a result of this process you're analyzing, it means that that process cannot happen. So how do we check to see if we're violating the second law? So here we have the rate form of the equation, and it's really this entropy generation term up here, sigma dot, that's going to tell us whether or not we're in violation of the second law. For real processes, we are going to know that sigma dot must be possible. For this to happen in the universe, we must be generating entropy. So the rate of entropy generation must be positive. The best we could ever hope to approach, but not necessarily attain, is this ideal process where the entropy generation rate is zero. Now, this is still impossible, but it kind of gives us the limit of what's possible. If we ever find a process, if we do an analysis where sigma dot is less than zero, it means one of two things. First, the process is not possible, or if we know the process is possible and we're getting a negative entropy generation rate, it might mean we made a mistake somewhere in the math. Now, last class, we looked at how to do a second law analysis on adiabatic processes, right? We looked at turbines and we looked at pumps, but a lot of times the problem or the more difficult part with the second law is adding this heat generation term, because first you've got to get the sign of the heat transfer right. And if you trust the first law when you're calculating Q dot, you'll get the right answer for this. But then you've got to pick the right temperature. There's two things about the temperature that we have to remember. The first is that because this is not a temperature difference, this temperature has to be in absolute temperature. So if you're doing metric, that means that it's Kelvin. And if you're doing imperial units, that means that it's Rankine. Second, this is not the temperature inside your control volume. This is the temperature, I think in the textbook it talks about it being the temperature on the boundary between the control volume, between your system and your surroundings. So oftentimes we will take the temperature outside your control volume or the surrounding temperature as a reasonable value for this T surroundings. So when this heat transfer term sticks around, you got to get the right Q dot, you got to pick the right temperature, and you have to pick the right units for the temperature. So when people make mistakes on exams or on quiz questions for this type of problem, it's because they mess up this heat transfer term. So we're going to show you how to do that today. So this, and maybe, we're cheating a little bit, we're jumping ahead, because this is a thermodynamic cycle, which we haven't talked about yet, right? But last time we took high pressure, high temperature fluid, put it into a turbine, and harvested some mechanical work, right? We got some work or power out of the turbine. And we looked at a pump where we went from this low pressure of the turbine, right? The turbine exit, you get some sort of, ideally it's still steam when it comes out here, that you haven't sort of had some condensation, because these turbine blades are whipping around really fast. You don't necessarily want little droplets of condensate inside your turbine because it can cause some damage inside the turbine. So you sort of want still steam coming out of your turbine, but it's low pressure, right? And because it's got less enthalpy in it, we kind of want to get back to this high enthalpy state so we can run the turbine again. Now, one of those processes, now we have steam, but we want to get to water, right? Because it doesn't take much power to increase the pressure of water. And then we need some kind of exothermic reaction. Usually this is burning things, right? Something like coal, but it could also be a nuclear reaction, right? Which generates a lot of heat. And then we put that heat into our high pressure liquid water to boil that water so we get back to the inlet of the turbine. So we've already done a second law analysis of the turbine and the pump, but what happens when we have heat transfer instead of, assuming a process is adiabatic? So we're going to look at that today, and specifically we're going to look at the condenser. If you remember, I was talking last class, when I was sort of talking to my brother about being a little bit worried about teaching this particular topic because it's confusing. And I was saying how the entropy always increases. But my brother made the point, which is correct, that here, right? Remember, now we're drawing this on a TS diagram. So we get vertical lines for ideal pumps and ideal turbines. But what we can see on this TS diagram, because we're moving this way, the entropy, the specific entropy of the liquid is decreasing, right? And that's a weird thing, right? So that means that in our second law, we also have this heat transfer term. So this heat transfer term in the second law has to be bigger. There has to be more entropy generated because we're adding heat to the system than there is entropy lost by cooling this down. This isn't as much of a problem when we're heating things up because here we're increasing the entropy, right? So we're going to look at the condenser here because this is the point where maybe we get a little bit of a problem, or at least conceptually you might look at this and say, oh, maybe here we're not generating entropy, right? So I'm going to show you that this is indeed a possible process. So here we have the condenser side of our heat exchanger. So we're coming in at state 3. State 3 is at 1 megapascal or as 1 bar or 0.1 megapascal, and the quality is 1, right? So this is the exit of my turbine. I have saturated vapor. And now my condenser, the purpose of the condenser is to condense this steam into liquid water. So when we leave our condenser, we have fluid that's coming out at the same pressure. So we're going to neglect any kind of losses from friction that would lower our pressure here. And we're going to assume that this is saturated liquid. So we've gone from saturated vapor to saturated liquid. Now, it tells us here that the temperature on the boundary, or the temperature outside, this T infinity means kind of far away from the boundary here. We're told that that temperature is 40 degrees Celsius. So this will take as the temperature of the surroundings, which we're using as a proxy for the temperature on the border between our system and our surroundings. We're also told the mass flow rate. So first we're supposed to find the heat transfer, or the rate of heat transfer, Q dot, and we're also asked, is this process, this condensation process, is it possible? Does it still have a positive entropy generation rate when we're performing this condensation process? So the first thing I'm going to do is draw my control volume. We've seen for heat exchangers that you can draw control volumes in different ways, but here, because I want to find the heat transferred, I'm going to only draw my control volume around the water phase, right? So there's something else that we're using to cool down this water so that it condenses. I don't even know what it is, so I guess I don't have much of a choice here, but it's a happy coincidence because it'll help me find this heat generation rate. So first I draw my control volume. I want to find the symbolic solution for Q dot. So the first thing that I have to do after I draw my control volume is conservation of mass. So when I do conservation of mass, this is not too bad because we have one inlet and one outlet. So we're going to say that this process is at steady state. I only have one inlet state, that's state 2, and one outlet state, state 3. So my summation signs here in conservation of mass are going to go away. And what I'm going to find is that m dot in is equal to m dot out. So for this condenser, I'm only going to talk about this as one mass flow rate. So I'll drop the subscripts and it's just m dot. And m dot is equal to 1 kilogram per second in this problem. Now that I've done conservation of mass, I can do a first law analysis. So I've already assumed that we're at steady state and that we're one inlet and one outlet. The next thing that I want to assume is that there are no fan blades inside my control volume so that this process is passive. Then I'll assume that the change in elevation is negligible. So that means that the change in the potential energy can be neglected. And we'll say the same thing about the change in kinetic energy. We'll say that that can also be neglected. And what we'll get is this Q dot is equal to m dot times h out minus h in. So this is hopefully not that surprising. This is what we would expect. So we're at a point, we want to know Q dot, but we don't know Q dot. But we're told mass flow rate, and we've showed that there's only one mass flow rate. It's the same, m dot in and m dot out are the same. I don't know h out, and I don't know h in. So I've got one equation and three unknowns, but that's okay because I've got some thermodynamic tables. So we'll fix the states to find these specific enthalpies. Now, because I'm going to look ahead and know that I'm also going to do a second law analysis here, I'll also look for specific entropies, little s. So I have my state table. State 3 and state 4 are given, right? So I think it actually in my state table, this should be state 2 and state 3. Sorry about that. So now here, we're moving from this point where we're at 1.1 megapascal or 1 bar, and we have a quality of 1, and we're moving to a point where we have the same pressure, but the quality is 0. So first we'll fix this state, a saturated vapor at 0.1 megapascals. So I go into table A3, I find my pressure. Now it's in bar, so I have to remember that 0.1 megapascals is the same thing as 1 bar. Now I look here, so this is the right row, and I want to find Hg, right? This is quality equal to 1, and Sg is also specific entropy when quality is equal to 1. So I'll put these two numbers into my table. Now I'm going to find state 3. Looks like here I fixed my my state table. This is 2 and 3, right? So now at state 3, I have a similar thing, but it's saturated liquid, right? So now my quality is 0. So I'll be looking for HF and SF. So now I'm going to go back to my table. It's still the same pressure, no interpolation required. I have HF and I have SF, and I can put those numbers into my table. So what I see here, and this is expected as we move from steam to liquid, we're losing enthalpy. There's less energy that's kind of stored in the mass here, but we're also decreasing the specific entropy. And this is kind of what we're maybe a little bit worried about because, my credibility is on the line here, right? Because I've been telling you that the entropy in the universe always increases, but this is the same thing my brother pointed out. The entropy of the water has decreased, right? So, but now we have enough information to find Q dot, and once we find Q dot, then we can move to a second law analysis, right? So the magic here is in the heat transfer. So we're going to find the heat transfer rate from our first law equation, right? We've already made some assumptions, and we know that Q dot is equal to m dot times HO minus HI, so H out minus H in, and in this case, that's H3 minus H2. I have numbers for all of these things, so I'm going to get m dot is 1 kilogram per second, right? Remember, I carry my units in my calculation. H3 is 417.46. H2 is 2,675.5. Both of those pieces of information, the specific enthalpies, are in kilojoules per kilogram. So now my kilograms are going to cancel out in this equation, right? Because one's in the numerator, one's in the denominator. I'll get kilojoules per second, which I know are kilowatts. In particular, I get 2,258 and change kilowatts. So now I know Q dot, right? That's pretty good, right? Because that was one of the things the problem was asking me. So now I've demonstrated that I know how to do conservation of mass, I know how to do conservation of energy, and if I put those two things together, I can find the heat transfer rate, the rate at which heat is leaving the water because of this condensation process. So I see here, right, and maybe I'm a little nervous about this, that the specific entropy has decreased from 7.35 to 1.3. So is this process possible? Because the entropy of the water is decreasing. But it's not really the entropy of the water that we're concerned about. Instead, this sigma dot term, this is the rate of energy generation in the universe, not in the water. Now, the water's part of it. We'll see here that the water's part of it, but this heat transfer term sort of tells us about the entropy generation that's going on in the universe outside of our control volume because of this process. So our surroundings are increasing in entropy because of this heat transfer, right? So is that enough that that we're going to end up generating entropy in the universe, right? So here we've already said that it's steady state and it's one inlet and one outlet. Here we can't assume that this process is adiabatic because we know heat transfer happens. That's the whole purpose of a condenser. So now, right, if we solve for, or we isolate sigma dot, right, this entropy generation rate, we're going to get negative Q dot surrounding. So this is the heat transfer from the system to the surroundings, right? The same heat transfer that we're going to solve for in the first law. We've already done that. And this is the temperature outside of my control volume, plus m dot times S out minus S in. The good news is we have all this information, right? So here, right, so this case, S out minus S in gives us a negative value, right? Now that's not necessarily great because here we want to have a positive value for entropy generation. So here we've got opposite terms. Now the question is, what's going on with this heat transfer term? So we know the heat transfer from the water is negative, right? So this is the value that I put in for Q dot. So I use the same heat transfer that I found inside my first law analysis. But this is negative of a negative, so this becomes positive, right? The other tricky thing here is I got to pick the right temperature. So this is the temperature outside my control volume, preferably on the boundary, but we don't have that information. So we're going to assume that T infinity is a good number to use here instead of the temperature inside my control volume, which I could find, right? Because I'm at 1 atmosphere or 1 bar, so a little bit less than 1 atmosphere. So I know the temperature inside my control volume is at about 100 degrees, but I have to be cooler than that outside my control volume because I'm cooling down this this water as it moves from steam into liquid, right? So there has to be some kind of heat sink here that's colder than my process that's going on inside my control volume. So I'm going to assume that that temperature is 40 degrees because that's kind of what the problem told me. But it's not 40 degrees Celsius, right? I have to turn this back into Kelvin, so I'll add 273 degrees Kelvin, right? So I have this term here. This is all going to be negative because 1.3 minus 7.36 is going to give me a negative number. But this number here is going to be positive because I have negative times the negative. So this number is going to be positive, and I'm hoping that for this process to be possible, that this term will be bigger than this term. So let's see what happens, right? So here I'm going to check my units, right, just to make sure I'm adding apples to apples. Always a good thing. So here my kilograms are going to cancel. I'll get kilojoules per second divided by Kelvin, right? And this is in kilowatts on the top and Kelvin on the bottom. So this is good. This looks to me like an entropy generation rate, right? So now this is kilowatts per Kelvin and kilowatts per Kelvin in the other term. So I can add these together. Now, what I see in this case is that I get 7.214 kilowatts per Kelvin. That's the rate that entropy is increasing because of this heat transfer term. And then the entropy decrease that happens because the water is decreasing in entropy as it moves from a vapor to a liquid is minus 6.1 kilowatts per degree Kelvin. So the total entropy generation rate is positive. So from that, I know that this condensation process is possible because I've checked that we passed the first law. I know that we conserve energy, and now I know that I'm generating entropy with this process. So I know that this whole process is possible. So this is one way to look at the second law. So we can look at the second law from a process to process state, and we can use a rate equation just like we've been using for conservation of energy. But like so many things in science and even outside of science, there's more than one way to look at this kind of a problem, right? So we've been looking at stringing these things together, right? And, you know, like I said, it's a bit of a spoiler here, but this is a heat engine, right? Because what this does is we're putting heat in to boil the water. So we get to this turbine and we produce power. Now there's some cost. So that power we get from the turbine is not free, right? So there's some power to run the pump. And we have to reject some heat here. But in general, we're adding heat. There's a net heat addition. And there's going to be some net work produced. So this is a heat engine. So I can zoom in on each of the individual components and do this rate version of the first law to look at what's going on. Or I can look at this heat engine as a whole, right? So if I look at this heat engine as a whole, what's happening is we're adding heat and we get net work out. So one of the ways we quantify these heat engines is we say, okay, so I got to burn some coal, right? And when I burn some coal, that adds some heat into my system. How much of that heat goes into net work, right? And so there were some people that looked at this, right? That, you know, and this probably happened somewhere around the time of steam engines where people were interested in, you know, how these heat engines kind of work, right? And there's this statement that the textbook talks about from Thomas Kelvin and Max Planck that says, it is impossible to construct a device which operates on a cycle, right? So that means it keeps operating, you know, at steady state and produces no other effect than the production of work and the transfer of heat from a single body, right? So I think what this version of the statement, at least what I think about when I read this statement, is that you can take heat, you can burn some coal, maybe burn some gasoline, right? And you can get some mechanical work. The problem is, because of irreversibilities, this engine that you have is going to get hot, right? So there's things like there's pistons moving up and down that are generating friction. And that heat has to be rejected somehow. But we can't reject that heat from the engine back to the hot reservoir. Because if we did, heat's got to go from hot places to cold places. So this engine can't get hotter than the hot place because then it would be rejecting heat to the hot place and you wouldn't be able to add this heat. So in order for a heat engine to work, you need to have a heat sink. So you can burn gasoline and make an internal combustion engine create work or power. But that engine's going to heat up, so you need to have a cold reservoir that's cooling it down, right? So you need to have some mechanism by which this engine is communicating with the universe, right, with the surroundings to cool itself down, right? And that happens, you know, through things like radiators in a car, right? So if we didn't have that, what would happen is the temperature of this engine would continue to increase and increase and increase, and then you end up in a situation that sometimes you see, unfortunately, on the side of the road is, you know, a car parked on the side of the road with its hood up, and it's just waiting there cooling off, right? Or maybe someone's trying to pour some water on it, you know, so if the radiator fails or something, right? You don't want to be in this situation, right? Because then your system, it was generating power, but it wasn't generating power in a cycle, right? It's not something that could have been performed over a long period of time because the engine got too hot and failed. So that's what this statement of the second law to me says. So is there another way to look at this, right? So we have this heat engine, there's heat coming in, there's work going out, and now we know that we need to have this heat sink somewhere inside of our system. So there's some kind of waste heat that's going to happen here. And this is unfortunate because ideally, right? So we'll end up talking about an efficiency here. In an ideal world, although we couldn't even get there in a thermodynamically ideal case, but the absolute best case scenario would be if we could take heat, put it into a machine, and turn all that heat into work, right? But that's not possible. It's not even, we can't even, that's not even the limit of what's possible because we have to reject some heat over here, right? So if we look at this whole system, right? So even though each individual component inside our heat engine here, right? This is what a very simple version of a coal-fired or nuclear power plant would look like. It's a series of open systems that are strung together, right? But if we zoom out and we draw our control volume at our orange dotted line, or even the dotted line, I guess, that's here in the textbook, right? We see that this is a closed system. Even though it's made up of a bunch of open systems, all the mass, right? So here I've got water going through my pump, through the boiler, through the turbine. It's all one inlet, one outlet, but they're kind of strung together, right? So it's a closed system if I widen my lens enough. So in a closed system, we could take the rate equation of a closed system. So we would get rid of, this is the same first law that we dealt with before, where delta E is equal to Q minus W, but we divided by delta T and took the limit as delta T approached zero, right? Or you can think of this as the open first law, but the mass flow rate terms go away because there is no mass flow rate in or mass flow rate out, right? So here, this is a closed system, and this is a version, this is the rate version of the closed system first law. If my system is at steady state, then what I get is that the net heat is equal to the net work. So if I add up all the heat that comes in and subtract all the heat that goes out, that's like my net heat, right? And I add up all the power that's generated by my turbine. But to get there, I had to plug this pump in, right? So I have to subtract the amount of power that's produced by my pump. And I get, at least when I talk about adding and subtracting, I guess I'm doing a little bit what the textbook does and says that these things are absolute values. But in truth, we know that the power produced by the turbine, the first law will tell us this is positive, and the first law will tell us this is negative, right? So really, I'm just adding them up, a positive number plus a negative number. Same thing with heat in. Heat in is positive, but heat out is negative. So really, I'm just adding these things up to get the difference in the magnitudes. And one will give me the net heat, the other will give me the net work, but they're the same. So Q dot in minus Q dot out is going to be equal to W dot net. So really what this means is that when I'm looking at a whole system like this, if I know the net work, I also know the net heat. Or if I know the net heat, I also know the net work. So this is good, right? So we're going to define this term, right? So this is called thermal efficiency. Now, maybe it's because I teach heat transfer, but sometimes, you know, I'll talk to people later on in their courses, and they'll be talking about, like in heat transfer, we do these case studies where people are designing systems and sort of analyzing their solution. And I'll ask a question like, oh, why did you pick that? And someone will say, oh, because it's more efficient, right? And I think that that's because colloquially, the word efficient has come to mean good, right? So I picked that one because it's more good, right? But because I teach thermodynamics, I kind of hate it when people use the word efficiency, but don't define what that efficiency is. Because in thermodynamics, we'll talk about several different types of efficiencies, and they're all fractions, and they all go between 0 and 1, or 0% and 100%, right? This is not sports where people think you can give 110%, right? A thermal efficiency, you can only ever get 100%, and actually you can't even get anywhere near that, right? As we'll see. So this is thermal efficiency. Now, for all of these different cycles, we're going to talk about a way to characterize the cycle. And generically, or generally, what we're going to say is that the cycle's desired energy effect divided by its energy cost to achieve that effect gives us whatever characterization parameter we're looking for. For heat engines, the desired energy effect, so the reason that I'm running a power plant is to generate power, right? And the cost that I pay is that I have to burn something or maybe perform some nuclear reaction to add heat in, right? This is also true for an automobile, right? For a car or for a jet engine. What we're trying to produce, at least for a car, maybe not a jet engine, because we'll talk about this, we're trying to produce thrust with a jet engine. But for a power plant or a car, what we're trying to get is mechanical power, right? The net work. That's what we're trying to generate, right? But the cost is that we have to add heat, right? So the cost is not net heat, right? Some of this heat we're going to end up wasting. That's how the universe works, right? We're going to try to waste as little heat as we can, and we'll learn different tricks how to do that for different cycles. But the cost is that we have to burn some fuel, right? Often fossil fuels, right? Although we're trying to get better at that, right? And that's part of the reason that we want to learn how to understand these systems, because when you understand something, right, this is kind of I think, the purpose of engineering is we try to understand how different systems work so that we can make them better. Even if we don't have a perfect understanding, we can still try to make systems better. So maybe you can get the same power out while burning less fuel, right? So how do we make things more efficient? And in that case, the efficiency that we're talking about is this thermal efficiency. So we know that, so this is true, network divided by heat in, right? But we know from looking at this first law analysis of the whole system that the net work is also equal to Q in minus Q out, or Q dot in minus Q out, if you want to talk about it from a rate perspective. So this equation, W dot net over Q dot in, is also equal to 1 minus Q dot out over Q dot in, right? And we can see that Q dot out, there is some waste heat, and Q dot in, so some portion of this heat in gets wasted, right, or goes to the heat sink. And we can see this is going to be a number that's less than 1. So our thermal efficiency is going to be 1 minus this, right? So now you may or may not have heard of an expression called a Carnot heat engine, right, or a Carnot engine. So this is not any particular type of engine. You can have Carnot engines that are nuclear power plants, Carnot engines that are internal combustion engines. When we put the word Carnot in front of something, what we mean is that this is an ideal engine, right? Now, unfortunately for us, the ideal engine is not one that has 100% efficiency, because we know that no cycle can run without communicating with another body, right? Without having this waste heat or this energy out, right? But what happens is, if we assume that the process is ideal, that all the processes in the system are ideal, we can approximate this Q dot out over Q dot in term as a ratio of the temperatures at the outlet divided by the temperature at the inlet. Now again, right, the hair on your back of your neck should stand up, because here we have temperatures that are not temperature differences. And anytime we see a temperature alone in an equation and it's not a delta T, what that means is that we have to use absolute temperatures. So we can get an approximation for the ideal heat engine if we take 1 minus T out minus, or divided by T in. We can check the units here. So this is a per unit value. It'll give us something between 0 and 1. That's like a percentage divided by 100, right? This is going to be 1 has no units, and Kelvin divided by Kelvin also has no units. So this is a dimensionless equation, right? So this is going to be a way, right? So this equation we could use if we knew the heat transfer rate from the ideal engine out and in, or the net work from the ideal engine and the heat in from the ideal engine. We could calculate the ideal engine this way too, right? But as a shortcut, if we knew the temperature that we're rejecting heat to and the temperature that we're adding heat in, then we can just use this equation to find the ideal engine. This analysis we can only do for Carnot engines or ideal engines. This equation we can do for real engines or for ideal engines. Now, ideal engines are always going to perform better than real or actual engines. So the ideal thermal efficiency is going to be higher than the actual thermal efficiency. This is another way, right? So one way to see that a process can't possibly happen is to do the second law analysis and see that the entropy generation is negative, right? We know that that means it wouldn't be possible. If you ever have a cycle and you do an analysis like this and someone is claiming that they get actual thermal efficiencies that are better than the Carnot efficiency for whatever engine you're talking about, then you know that that's not possible, right? That they must have made a mistake, or, I mean, maybe they're more nefarious and they're just, not telling the truth. So here's a heat engine example, right? So here we have this heat engine, right, which the textbook draws as a box with a circle in it, right? And we have this hot reservoir and a cold reservoir. We know that the hot reservoir is 50 degrees Celsius and the cold reservoir, or hot is 150 Celsius. The cold reservoir is 50 degrees Celsius. We know that the heat transfer rate in is 100 kilowatts. What's the maximum possible outlet, or what's the maximum possible net work that we could generate from this system? So we know that the maximum thermal efficiency, the Carnot efficiency, is going to be 1 minus T cold divided by T hot. But we know that those temperatures have to be in Kelvin. They were given to us in Celsius, so we convert those. And here we get that the thermal efficiency in this case, the maximum thermal efficiency in this case, is 0.24 or 24%. So that means the most we could ever get out of this 1,000 kilowatts of heat transfer that we're putting in, the heat transfer rate of 100 kilowatts, the best we could do is 24 kilowatts of work, right? So I take this, I know that the thermal efficiency is 0.24. That's going to be the net work divided by the heat transfer rate in. I take the heat transfer rate in multiplied by 0.24, and I get the 24 kilowatts, right? So this is with the perfect system, right? So I know that, when we think about grades and courses and things, we think about, the maximum that we could do is 100%. And that's true in a class like this. It's not true when we're talking about heat engines, right? So this thermal efficiency is governed by the hot temperature in your system and the cold temperature in the system. A lot of times, the cold temperature in the system is fixed by whatever environmental temperature you have in your system, because most of the time we're venting heat to the atmosphere. The hot temperature in your system is, we need some chemical engineers to make fuels that burn really hot. We need some materials engineers to make components that don't melt at high temperatures, because let's say I can get a turbine, I can get fluid running into my turbine or my boiler, right? Because that's probably going to be the hottest place. And I have a fuel that burns very, very, very hot. But if the steel that makes up the boiler melts at a temperature below whatever combustion temperature I have for that fuel, then I'm not going to have a cycle that lasts very long, right? So to make good cycles, we need help from all of our friends in engineering, right? So here, right, because this maximum thermal efficiency is going to be 1 minus T cold over T hot. So if I could reduce T cold to very cold, or if I could increase T hot to very hot, then my thermal efficiency would go up, right? But in this case, 0.24, right, or 24%. Now there's another way that we can look at the second law, and this is called the Clausius statement of the second law, named after Rudolf Clausius, right? And what it says is it's impossible to construct a device which operates on a cycle whose sole effect is transfer of heat from a cooler body to a hotter body, right? So what this means, I think, because again, when we just look at the words, I think it's sometimes hard to explain, right? So you know that we can make machines that transfer heat from a place that's colder to a place that's hotter. You know this because probably you've used a refrigerator, right? And the refrigerator, let's say in your fridge, maybe it's 4 degrees Celsius or something inside the body of your fridge. And you know that in your room, it's maybe 20 or 21 degrees Celsius in your room, and yet the refrigerator removes heat from inside the fridge and expels that heat to the room. And the way we do that is we build a machine where the cold side of so this machine here has a cold side down here and a hot side over here. And the cold side is colder than the thing you want to keep cold, and the hot side is hotter than whatever room you have that you're pushing heat into. So this is kind of cool because this is a great example of how, by understanding physics, right, and engineering, we were able to kind of bend the universe to our will a little bit and make it look like we're violating what my heat transfer professor used to call the 0th law of thermodynamics, that heat always travels from hot temperatures to cold temperatures, right? And that's still true. It doesn't look like it in this machine because it looks like we're transferring heat from this cold place to this hot place. But really, we made this side of the machine colder than here, so we're transferring heat from our cold side, which is hotter than the cold side of the machine. And then we have a hot side of the machine, which is hotter than our exterior temperature, right? So what this means when it says that its sole effect is the transfer of heat from a cooler body to a hotter body, I think what it's talking about is it's not just the heat transfer that matters here, right? So we can't create a machine that's transferring heat from cold places to hot places and producing power. We can't even produce a machine that transfers heat from a cold reservoir to a hot reservoir that has a network of 0. One of the things that you probably know about your refrigerator or your air conditioner is that you have to plug it into the wall. So in order for us to make a machine that transfers heat from a cold reservoir to a hot reservoir, we have to add mechanical work. So this is sort of the opposite of a heat engine, whereas in a heat engine, we're putting in heat to generate work. In this kind of a system, something like a refrigerator, we're putting in net work so that we can sort of trick the universe into moving heat from a colder place to a hotter place, right? So here we have another characterization parameter, and it depends. So we can have a heat pump or we can have a refrigerator. And the difference between a heat pump and a refrigerator from a thermodynamic perspective is where you are, right? So here, right, if you're a person that's sitting in the hot part, you have a heat pump, because the purpose of a heat pump is to heat up the hot side, right? So this is kind of like if you had a heat pump that was heating your house in the wintertime, it's cold outside, but you're trying to push heat into where it's hot, right? So your perspective is sitting here on the hot side, right? So yes, we can do this, right? And a heat pump is transferring thermal energy from low temperature outside to a high temperature, which is inside, right? So Clausius tells us, the Clausius statement tells us that it's not possible to build a heat pump that does not require usable work as an input, right? So you have to put work into the system for it to happen. Now, we can characterize this kind of a cycle too, but we cannot call it an efficiency, because we'll see that oftentimes these characterization parameters get to be more than one. And I told you that we can't have, it's not like sports, there's no more than 100%, right? So here we have something called a coefficient of performance. So if you have a coefficient of performance for a heat pump in the real world, this is going to be gamma actual, right? And this is, again, all of these characterization parameters are the desired energy effect divided by the energy cost to achieve that effect. So if you're doing a heat pump, your desired energy effect is to add heat to the hot place. So this is the heat transfer rate into the hot place. And the cost is that you have to plug this thing into the wall. So there's some net power that you have to add to the system. So the coefficient of performance for heat pumps is equal to gamma. You don't have to remember, if you don't want to remember the different Greek letters on tests and things, you can just put coefficient of performance, right? Specify that it's a heat pump in the superscript, and whether you're talking about actual or ideal in the subscript, right? So here we're going to have Q dot hot over W dot net. We know that W dot net, because this is a closed system, is Q dot hot minus Q dot cold. So this is true for ideal systems, but also true for actual systems. But if we'd like to do this for ideal systems, we can substitute our heat transfer rate terms for temperatures, right? We see that it's a delta T on the bottom, so I could use Kelvin or I could use Celsius. But on the top, this has to be in Kelvin. So I'm going to tell you, if you're going to do these kind of calculations, it's probably better off always to use Kelvin or Rankine, and then you know you won't mess it up, right? So this is the ideal coefficient of performance for a heat pump. T hot divided by T hot minus T cold, or Q dot hot over W dot net. Again, in the numerator especially, we always want to use absolute temperatures because that's a temperature that stands alone. It's not a delta T. So the Carnot heat pump is just an ideal heat pump. Carnot heat pumps are not real, right? It's like the tooth fairy. We can't ever get to that performance, but we can sort of asymptotically approach it, at least theoretically. And it shows us how performance changes as we change the temperatures, right? So even though this equation, you know, some people might say, well, it's a useless equation because we can never get to that level of performance. But looking at this equation tells me how I can change T hot and T cold to try to get better coefficients of performance. We can also look at coefficient of performance for refrigeration units. Right now, if you're trying to run a refrigeration unit, right, maybe you're trying to keep your house cold in the summer, then what you're trying to do, the thing you're concerned about, the energy benefit, is removing heat from the cold place, right? So refrigeration cycles are transferring energy from a low temperature to a high temperature, just like a heat pump. But the difference is the benefit that we're worried about is how much heat we're removing from the cold side, right? And again, the Clausius statement tells us that we can only do this if we're adding work to the system. That's why you got to plug your fridge into the wall. Again, we have a coefficient of performance for refrigerators. This time, our Greek letter is beta. I try to remember this because beta looks a little bit like an R, and R is for refrigeration, right? It's not perfect, but it definitely looks more like an R than a gamma does. So here, again, we have the desired energy benefit divided by the energy cost. So here, because we're in the refrigerator, right? So now we're standing on the cold side, and what we want to be able to do, our benefit, we want to remove heat from the cold side, and we'd like to, or we have to add work to do this, right? So this looks just like the coefficient of performance for a heat pump, except in the heat pump, our energy benefit was that we were adding heat to the hot side, and here we're removing heat from the cold side. Again, we can use our first law on the whole system to show that W dot net is equal to Q dot hot minus Q dot cold. If we look at the Carnot coefficient of performance for refrigeration, right, we turn the Q dots into temperatures. Again, I have a temperature that stands alone up here, so I need to use absolute temperatures, right? The difference again is that it's the cold temperature that's on the top because in the refrigerator, we're interested in the cold side. Again, we want to worry about absolute temperatures here. So Carnot refrigerators are also not real. You can never have a Carnot refrigerator in your house, but having this equation, again, tells us some parameters we can tweak to try to get better performance. So even though this is an imperfect model, engineers could still use this to try to get better performance out of an existing component like a refrigerator. That's all that I have for you today. Thanks for joining me on Thermodynamics.